this video, we present our method for dual contouring Hermite data. This footage was captured on a consumer-level PC in real time. We begin with a simple example of a mechanical part. An implicit description of the part was generated from a subdivision surface via a scan conversion algorithm. Here you can see the underlying uniform grid that describes the surface. Vertices of the grid are signs represented here as spheres and boxes, for inside and outside respectively. Those edges that contain a sign change are tagged with an exact intersection point and a normal shown here in green. Polygon generation proceeds in two steps. First, our method constructs quadratic error functions for each cube from the Hermite data on its edges and calculates one vertex per cube at the minimizer of the quadratic error function. Next, for each edge in the grid that exhibits a sign change, our method generates a quad whose vertices are positioned at the minimizing vertices from the cubes containing that edge. Here we see a tempo model defined using the 256 cube grid. This grid is represented as an octree, with the empty and solid space collapsed maximally, and mixed leaves inherited from the uniform grid. We now simplify this model to an error of 0.014 and collapse interior nodes using the quadratic error function. Our new numerically stable representation for the error functions enables us to collapse all of the flat areas immediately. Now we show the same stage of simplification computed using the standard unstable representation for quadratic error functions. Note that the initial collapse fails to simplify some of the flat regions due to numerical error. At this error level, there are more than twice as many polygons as produced by the stable method shown earlier. We continue our simplification of the tempo using the numerically stable representation for the quadratic error function. We repeatedly collapse the model until we reach a very coarse level. Note that the letters are still topologically equivalent to the original letters due to the use of a topological safety test that we have developed. The columns as well as the ring on top of the temple also maintain their topological shape. Here we have added Michelangelo's David to the temple to illustrate a complex polygonal model. This model has already been simplified to a reasonable number of polygons. We modeled different solid regions using a multi-sign representation. Empty space is one sign, while distinct solid regions are modeled as different signs. We generate one contour corresponding to empty solid regions and texture those polygons by the solid's properties. For example, the text Siggraph is a solid extending through the back wall of the temple. In this representation, all CSG operations are additions. Subtracting a sphere from the model is equivalent to adding a sphere of empty space. Note that the solids are true volumes, since the distinct solid regions extend into the interior, as is evident by the cuts on the letters. Here we add solids to the model. We can also replace solid regions of the model with different materials, seen here as a blue solid. Dual contouring is a fast, simple method for contouring Hermite data. It supports polyhedral simplification through the use of quadratic error functions and topological safety of those simplifications.